Hello and welcome to this demo. Today we will be looking at a car seat and how to flatten it using ExactFlat for Rhino. To begin, we're going to make sure that we've got our model here is one single poly surface, and the reason we make sure it's a single poly surface is for meshing purposes. Although ExactFlat can flatten surfaces in any kind of mesh, by creating the mesh ourselves we get a better degree of control over how the flattening process occurs. And when we create a mesh from a single poly surface, we can be sure that all the boundaries of the individual surfaces, when we look at the perimeter of our piece here, we can make sure that the mesh edges all align along the perimeters. Whereas if we explode this into individual surfaces and create a mesh from it, we may not have an aligned edge along here. So by meshing this as a single poly surface, we make sure that all the boundaries, all the internal boundaries, they all have shared mesh edges, and it creates a better mesh for us to work with. So to begin, we're going to select our mesh here, and we're going to go ahead and we're going to use the Rhino mesh command to create a new mesh. The easiest way to do this is to use the simple controls and drag the slider all the way over to more polygons, and when we do this we get a fairly complex mesh, and this works fairly well for this car seat model, but some models it doesn't work so well. So what we can do is we can go to detailed controls, and we can just kind of by moving the mouse around, we can get a sense of scale. This model's in millimeters right now, so we can get a sense of scale and create a mesh that has a fairly fine triangulation or quadrangulation. So as we move our mouse around here, we'll start high. We're going to set our maximum aspect ratio to 2. We're going to set our minimum edge length to, we'll set this to 0.2, and we'll set our maximum edge length to 2. And if we hit preview, we're going to see a preview of the mesh. This may or may not be a good mesh, and this is far too many quads or triangles, so we're actually going to increase this. So we're going to change this to 10 and minimum edge length of 1, and we're going to hit our preview again. So now we've got a mesh that looks like it's going to be a very good starting point for the adaptive remesher. We can see all the quads in here, and we don't have any scenarios where we've got very, very large triangles mixed in with very small triangles. So this is a good point. So we're going to click OK. Best practice is always to separate out your surfaces and meshes. I like to keep copies of all the geometry as we're doing the flattening. That way, if there's a problem with any of the geometry, it's very easy to go back and recover from our mistakes. So I'm going to create a new mesh layer here. I'm going to select our mesh, and I'm going to put it on the mesh layer. That way, any repairs I do, I can do them to the mesh layer, and I'm not going to have to worry about recreating the mesh. I can always come back to my original mesh. So we've got our mesh on the mesh layer here, and we're going to turn off the surface now. Now we don't want to flatten this as a single mesh or a single surface, a poly surface, because we're going to be sewing this together. So we're going to have a couple different seams here. So what we're going to do is we're now going to explode our mesh into individual components. So we end up with 16 meshes after exploding. I can now select the individual faces by holding Control or Shift, and now I'm just going to join these together. So we're joining 6 meshes into one mesh. We're going to join the front together as well, and for this one we're going to join the back together as well. So really what we've done with joining is we've taken 4 unique collections of vertices and triangles, and we've just joined them into one container, but that single container still contains 4 unique collections of vertices and faces. So what we're going to do is we're going to use the Rhino weld command. What this is going to do is it's going to find all those duplicate vertices, and it's going to merge them together. So we're just going to rectangle select everything, and we're just going to use the Rhino weld command. So we're going to type it in, and we're going to use an angular tolerance of 180 degrees. So now we've welded everything together. And the next step is to remesh, but before we do that, we're actually going to use the ExactFlat Mesh Validator to ensure that we don't have any kind of geometry problems with our mesh. So to do this, we're going to switch over to the Mesh Tools tab of the ExactFlat toolbar, and we're going to use the very first tool here, the Mesh Validator. and it's going to check all of these pieces to make sure that there aren't any geometrically degenerate triangles or topologically degenerate triangles or any other kind of meshing errors, duplicate vertices, incompatible face orientations, etc. In this case, it's telling us that all the selected meshes are valid, so we don't have any problems with our geometry. We can proceed on to the adaptive remesher. So once again, we're going to rectangle select everything. We're going to go to the adaptive remesher. And before we change any settings here, we're just going to go ahead, we're going to click the Start button, and we're going to inspect the default results. So for all our meshes, we're starting off with a couple thousand vertices, and over on the right hand side here, ExactFlat is telling us the estimated vertex count. So in this case, the adaptive remesher has performed its function very well. We've decimated the mesh, so we've greatly reduced the triangle and vertex count of the mesh, and we can see we've also preserved the shape and fidelity of the pieces. So this mesh looks fine. If we wanted to preserve a bit more detail, we could lower the desired tolerances, so we'll try changing these all to 6. So we're these tolerances, what they are is they're the maximum allowed distance between the original mesh and the new mesh. So we can have the maximum allowed distance between the surface of the triangle faces and the boundary. So if we need more detail to be preserved, we want to lower these values. We don't want to allow as much of a distance, and that's going to create more triangles, more vertices. So we've changed these from 8 to 6. Now we're going to click Start again. And we're going to notice that we're going to have a higher triangle count or vertex count now for most of these pieces here. So we're preserving a bit more of the detail. Once we're happy with our mesh, we can go ahead and we can click OK. And now we've got our adaptively remeshed mesh here, and it's ready for flattening. To flatten, we're going to switch to the Tools toolbar of the ExactFlat toolbar. And we're going to go ahead, we're going to use the very first command here, and this is the Flatten command. So with ExactFlat, ExactFlat is a two-stage flattener, the first stage being our pre-flatteners. So when we use the Flatten command, we're actually using a pre-flattener to create our initial flat pattern. And the pre-flatteners, they're very, very fast, but they are not optimized or perfect patterns at all. And we can see this because we can, when we look at this pattern, we can see that all the pieces have a fairly high strain on them. And in the case of this piece here, we have a flip triangle or a fold or wrinkle, and this is indicated by the cross here. And if we actually zoom in, it's incredibly small, but normally we'd be able to see the inset triangles on this piece as well. So we do have flip triangles here that are patterning problems that need to be fixed. Before we proceed, though, we're going to minimize our perspective viewport. We don't want to be able to rotate everything around. Our flat patterns are flat, so if we rotate the wrong way, we're not going to be able to see them. So there's a better view to use, so we're going to minimize our perspective viewport, and we're going to maximize our top viewport. And I'm doing this just by double-clicking on the viewport title. We're also going to make the ExactFlat pattern layer. We're going to make this our default layer by adding a check mark beside it. And we're going to turn off the other layers, the ExactFlat model and the mesh layer, by turning off the light bulbs. Now we're only looking at the pattern piece, and we're looking at it in a top-down view. So the first thing we're going to do, the last step with ExactFlat is always our second stage flattener, our optimizer, and that's the spring icon here. But before we do this, we're going to use a couple of our pre-flatteners, our first stage flatteners, and the goal of the pre-flatteners is first and foremost to eliminate flip triangles. So we do have a flip triangle here. So we're going to use a pre-flattener to remove this flip triangle. And our second goal is to minimize strain and sag as much as possible. Because they are very, very fast pre-flatteners, it's much better to eliminate as much strain and sag as possible using the pre-flattener and then finish the job using the optimizer. The optimizer, the performance and the amount of time required to use the optimizer depends entirely on the shape and the amount of strain present in the pattern piece being optimized. So if we can use a very fast pre-flattener to reduce the strain before optimizing, we're going to save a lot of time when we start using the optimizer. So we're going to use, for these pieces, we're going to use the ExactFlat fracture flattener. A lot of these pieces are symmetrical or near developable, so fracture tends to work very well for them. So for this piece here, I'm just going to pick a spot in the middle, and we can see that we've removed most of the strain, and we've also removed the flip triangle. I'm going to repeat the process for the remainder of the pieces. For this one here, we've actually created some additional flip triangles, so I'm going to try fracturing from a different location. I'm going to choose a location down here. We still have a flip triangle down here at the end, so there we go. We've been able to remove it. We'll just repeat this process for the rest of the pieces here, and you'll notice that as I pick different locations, our shape is changing, the strain is changing. For this one here, it's we still have flip triangles, so I think we're just going to use our pelt pre-flattener for this one instead. We don't get as nice a shape, but we do remove the flip triangles, which is the most important goal of the pre-flatteners. So we'll continue on with our fracture pre-flattener. And we're just going to finish up with the pieces here. So now that we've eliminated most of the strain and sag and removed all the flip triangles, it's time to use our optimizer to reduce the strain and sag to as close to 0 as possible. So we're going to click the spring icon here, and we're going to select all our pattern pieces, and we'll press enter when we're done selecting. And we're going to go ahead, we're just going to use the default settings here. For this, we're going to optimize with a cotton material. However, if we do need to change our material, we can do so by clicking the Browse button. And this is going to open up the ExactFlat model browser, or material browser. ExactFlat comes standard with about 85 different materials in the list here, so you can choose from any of the materials. If you are working with a specialty material that is not representative of any of the materials in the ExactFlat default library, then it is possible to have your material measured and analyzed, and then you can create a mathematical model of your material. We do offer our services through a partner of ours, through a university. The cost is about $25 US, and in about 5 business days they are able to measure and mechanically measure the properties of your material, and they will generate a report and send it back to you that you can then use to create a material model in ExactFlat. So it's a very inexpensive way to get your own material into ExactFlat for use with the ExactFlat optimizer. So we're going to go ahead, we're going to click OK. We're going to see our pieces are starting to optimize. So we've already optimized our first piece here, and as they're optimizing, we're going to notice that the shape and color of the pieces are changing. So the shape is changing as we're adding and removing material to create the best fit possible, and the colors are changing to indicate the change in the amount of strain on the pattern piece. So we're noticing that they're all changing from greens and blues. They're all shifting towards lighter colors, towards white. So with ExactFlat, the colors represent the amount of strain on the pattern piece. So if we think of our 3D shape as a rigid model, the strain indicates how much we're going to have to stretch and pull our 2D pattern piece to get it to fit back onto the 3D model. So the more strain we have, the more we're going to have to pull our pattern piece. In reality, what this means is the more strain we have, it just means our pattern piece is too small. So we're going to have to either expand it, make it bigger, or really pull on it hard. So for materials like a spandex, you probably do want to see some strain. That way it's nice and tight. But for other materials, especially rigid materials like leather and steel or wood, you don't want any strain because you can't stretch them. For those pieces, it's even more important that your perimeter length is the same, or your seam lengths between pieces. That's probably the most important part there. So to help with that and the strain, the spring status report that we're currently looking at provides some very useful information to help you determine the fit and accuracy of the pattern. So the most telling piece of information is the average energy density. We're done optimizing all our pieces here, but we can go back and view the optimization report for all the pieces here. So the most important piece of information is probably the average energy density. So this is the total average amount of energy or strain present on your pattern piece after optimizing. So for this one, we've got about 0.1 Newton meters of strain, which is not a lot of strain at all. So, and we can tell this just by looking at the color too. So we don't see a lot of strain on here. We only see a tiny bit of blue here, which indicates to us that we've got less than 5% strain on this pattern piece, and we can see this from the average energy density as well. Another useful piece of information is the maximum energy density. So this is the maximum single point of energy that has the absolute most energy left on the pattern piece. So in a lot of cases this may just be an internal anomaly or a meshing error, but generally speaking the maximum energy density is not much higher than the average energy density, and this is just another piece of information to indicate to you how good of a fit your pattern is. The last piece of information we want to look at is the no seam stretch error. And this is the linear difference in distance between the 3D model perimeter length and the 2D pattern perimeter length. So in this case it's telling us that we've got either our pattern is about 16 millimeters shorter or 15 or 16 millimeters longer than our 3D model length. So this on its own isn't all that important. However, when we start considering this in terms of sewing neighboring pattern pieces, the closer to 0 this value is, the better. So really this value has to be taken into consideration with the size of the model. So this is a car seat, so 15 millimeters around the entire perimeter of one of these pieces is a very, very small value. And when we start comparing the actual edge lengths that are going to be sewn together, that's generally a better indicator for fit. But so far for this piece, our entire perimeter length is the boundary length here, we've about 1500 millimeters, and we've got a difference of about 15 millimeters between our 3D model boundary and our 2D pattern boundary. So that's a very good indicator that this is a very good fit. So we're going to go ahead, we're going to click OK. And we're going to start to arrange our pattern now to make it a little easier for adding notches, and for when we create our DXF, it's going to make it a little easier to visualize how this pattern goes together. So to arrange this pattern, I'm simply going to use the Rhino rotate command. I'm going to rotate this pattern piece to an orientation that we already know is correct. So I'm going to select our 2 points here, and just holding Shift on my keyboard, I'm going to lock this secondary reference point to the horizontal x-axis, and I'm going to rotate the piece so it's perfectly up and down. Next, I'm going to use the ExactFlat Find tool to find my neighboring pattern piece. So I'm just going to, again, move my mouse around here to get a bit of a sense of scale. So based on this, I think an offset of about 100 is probably good. So as we start moving our cursor along one edge, we're going to see an orange or brown highlight appearing. And if we look at the piece just up here and to the right, as I move my cursor along the edge, we're also seeing the neighboring edge being highlighted here. So when I click on this edge, ExactFlat is going to find and rotate that piece to the selection point. And ExactFlat actually knows how all these pieces sew together. It determines this from the flattening process from the 3D model. It's going to build edge references and associations during the flattening process, which we can now make use of in the patterning process. So this is very useful for relaying or laying our pieces out and rearranging them. And now we can also actually add seams and notches to this piece too. So we're going to add some notches using the ExactFlat Notch Tag tool. And the way we're going to do this is we set our default notch, and with the way this is set up, the %n letter combination just simply represents a unique auto-incrementing number. So our notch tags are just going to be a simple number. We're going to add a slit notch. We can either add slit notches or V notches, and we can also modify the length and width. When the length is set to 0, we're just creating a notch that is the same length as the global seam allowance that's going to be applied to the pattern piece. So we're going to go ahead, we're going to click Add, and we're just going to start selecting vertices along one edge here. And we're going to notice that as we choose a vertex here, it's automatically applying the same notch to the same side on the opposite piece. So we'll just add a few vertices along this edge here, and we'll do the same thing over on this piece here. So once we've added all of our notches to all the pieces, we can then either save this file for use in Rhino if you want to add your own seams, or we can create a DXF. Depending on your downstream processes, if you're bringing this into a package such as AccuMark or Optitex, you may want to create a DXF that doesn't have any notches and doesn't have any seam allowance, and then you can use a third-party package for creating your seams and patterning information, or you can use the ExactFlat patterning tools such as our notch tags and piece tags, and you can add a seam allowance to the DXF to do your patterning work. So with ExactFlat, we're just going to have a quick look at our options here. And if we expand the Add ExactFlat section, we're going to go to DXF Export. Right now we're going to create our DXF. We're going to export it as polylines, although we do have the option to export it as arcs and lines as well as splines and lines. We're just going to export it as polylines, and we're going to create a seam allowance of, right now we're working in millimeters, so we're going to add a seam allowance of 10 millimeters to this piece. So now to create a DXF is a fairly simple process. We're just going to click the DXF button in the ExactFlat toolbar, and it's going to create a DXF for us. So it's asking us to choose a location for the DXF. So we're just going to, we're going to give it a file name of seat, and it's going to create the DXF for us. So now we're going to import this seat. And now we can have a look at the seat compared to the ExactFlat pattern pieces. So we've added notches to this middle piece, so we'll drag this over for a comparison. And we can see that the perimeter matches up fairly well. And every single place we've added a notch with ExactFlat, we can see the corresponding notch in the DXF. So we'll just move this over here, and I'm going to use the move command. I'm going to move this pattern, or this block piece from this point to this point here, and now everything should match up exactly. So when we look at the layer structure of the DXF, we've got a couple different layers here. We've got our grain layer, which is always going to be the horizontal x-axis. This grain line can be changed. If we want to manually set a grain line, we can do that using the grain tool here. So to do this, we just turn on the tool, and now we can select an edge, any edge on this pattern piece to act as our grain edge. Part of this tool is also our global target strain system. We're not going to add global target strain to this piece, we're just going to go ahead and click OK. So if I were to recreate our DXF, the grain line for this piece, right now it's the horizontal x-axis. If we were to recreate this DXF, the grain line would now be more aligned with this bottom edge here. So we've got a separate layer for the grain line. We have a separate layer for the cut line. So in this case, it's the red line. So your cut line is always going to be your seam line plus the optional seam allowance. So in this case, we added 10 millimeter seam allowance, and we can verify this using the distance command. So we're going to determine the distance between this point here and this point right here. It's 10 millimeters, so we can verify that the seam allowance is correct. So we've got a separate layer for our grain line, and we can turn that on or off. We've got a separate layer for our cut line, we can turn that on or off. We also have a separate layer for our seam line, so that can be turned on or off. And we also have a separate layer for our notching and our notch tags. The notch tag is going to be unique text that's created for every single notch. So we've got number 10 there, and we've got number 11 up here. So the notch tags are placed on separate layers from the actual notch geometry itself. So in summary, we started off with our surface. We created our mesh from our surface. Let's go ahead and I'll turn off the DXF here. So we started off with our surface. Once we had our surface, we went ahead, we created a mesh from the surface. Once we had our mesh, we went ahead and we used the ExactFlat Adaptive Remesher to recondition the mesh. So when we used the Adaptive Remesher, we've decimated it, and we've also simplified the shape of the triangles on it. Once we did that, we were able to flatten our mesh, and we ended up with our patterns here. So the first stage flattener is the first button here. It does a pre-flattener to the pattern pieces and produces unoptimized pattern pieces. After we remove the excess strain, sag, and flip triangles using the pre-flatteners, we then optimized the pattern pieces using the spring tool, and then we rearranged our pattern pieces using the rotate and move commands. So we first selected one piece, we rotated to the orientation that we wanted. We then used the find tool to snap all our neighboring pattern pieces to the edges. And once we were done that, we then used our notch tag tool to add notches all the way along the end. And then we created a DXF from our pattern using the ExactFlat DXF tool.